Welcome back for Chapter 6 note. We are actually going to take us back a little bit into the end of Chapter 3, where we learned how to calculate a z-score. A z-score tells you how many standard deviations the value is above or below the mean. Okay. So in Chapter 4 and 5, we learned about probability, and we learned about a probability binomial distribution. So now going back to quantitative data and quantitative continuous data, we're going to tie in a z-score, and we're going to learn about a distribution that is for quantitative continuous data. So just refreshing on our calculation of a z-score. Suppose that x is symmetric with mean mu equals to 5 and standard deviation of sigma 6. Suppose x is equal to 17. So if x is equal to 17, to find the z-score, we're going to take 17 and subtract the mean and then divide by 6. And when you type this into the calculator, make sure that you're putting those into parentheses. So this becomes 17 minus 5 is 12 divided by 6 is 2. So this means that x equal to 17 is 2 standard deviations above or to the right of the mean 5. Now suppose x equals 1. That means that z equals 1 minus 5 divided by 6, which equals a negative 0.67. And I'm going to share my Desmos screen so that you can see how this is calculated. So in Desmos, we're going to put in parentheses 1 minus 5, and then hit divide, and you can see that then it creates a fraction and gives you the correct decimal, or you can click on the circle here and it will put it into fraction form. This means that x equal to 1 is negative 0.67 standard deviations below or to the left of the mean. So summarizing this, when z is positive, x is above or to the right of the mean. And when z is negative, x is to the left or below the mean. The standard normal distribution is a normal distribution of standardized values called z-scores. And this is the calculation of that. We are not going to do any of this on our own. We're going to let a program in Desmos calculate this, or a command in Desmos. And similar to what we did in Chapter 5 with the binomial distribution, we're going to have a normal distribution command in Desmos to calculate this. But this normal distribution uses the idea of the empirical rule. So let's just summarize some properties of the normal distribution. A normal distribution is bell-shaped. So that's where it's similar to the empirical rule. The mean, the median, and the mode are equal and are located at the center of the distribution. So if it's normally distributed, where we can use the empirical rule, then this should be true. A normal distribution curve is unimodal. There's only one mode. The curve is symmetric about the mean. So that means that half of the data should fall to the right and half of the data should fall to the left. The curve is continuous. That is, there's no gaps or holes. For each value of x, there is a corresponding value of y. The curve never touches the x-axis. Theoretically, no matter how far in either direction the curve extends, it never meets the y-axis. It never meets the x-axis. But it gets increasingly close. Those are called asymptotes. The total area under a normal distribution curve is equal to 1 or 100%. This fact may seem unusual since the curve never touches the x-axis, but one can prove it mathematically by using calculus. We're not going to do that this semester. And lastly, the area under the part of a normal curve that lies one standard deviation of the mean is approximately 0.68 or 68%. Within 2 standard deviations is approximately 95%, and within 3 standard deviations is about 99.7%. This should look very familiar to what we learned about the empirical rule back in Chapter 3. Okay, so you'll see there's 34.13% and 13.59%. So the percentages are slightly different than what we learned in the empirical rule, and that's okay because again, we're mostly letting Desmos do the calculations. So just like in chapter 5, there was a notation for the binomial distribution, we're also going to have a notation for the normal distribution. And that notation is X is normally distributed with mean mu and standard deviation sigma. And our z-score is found like this: the X observation subtracting the mean divided by sigma. And so our normal distribution has a particular symbol notation, and that's X is normally distributed with 0 and 1. So the normal distribution has a mean or center at 0, and its standard deviation is 1. So that means at 1 standard deviation, there should be approximately that 34% that falls above the mean and 34% that falls below the mean. And then a -2 and a -3 and a +2 and a +3. And those should follow, sorry about that, those should follow similar to what we learned in the empirical rule. At the top here, the page of notes, it just kind of goes back through the empirical rule and what we learned about the percentages of the data that fall between them. So there's 2 ways that we can interpret this. So we could say that 34.13% of the data values would fall below the mean, or we could also say that there is 34.13 probability that a single data would fall 1 standard deviation below the mean. So you can either talk about a group of data values, or you could talk about a single data value. And so that's interpreting your percentage in 2 different ways, but it means the same thing. So when we look at the shaded area in the following graph indicates the area to the left, or the probability that X falls below this value. Okay. We're also going to be using the complement, because sometimes we'll be talking about a left area, but we want to know about the right area. Sometimes we'll be given the right area, but we want to know about the left area. So we might have to use the complement to do that. Okay. And the delta command that we're going to be using is going to be normal dist 0, 1 if we're talking about the normal curve. And then remember, we're going to be talking about cumulative. One thing is different with the normal curve because it's continuous. We can never land at an exact X value. We can be less than an X value, greater than an X value, or between 2 X values, but we can never actually land at an exact X value. So just as a reminder that we are going to use the normal distribution when we want to find probability. The probability or percentage of values or area. So remember, this up here is area, percentage values, or probability. And down here is where we mark the X value or the Z value that we have been given. Okay, so it's important that when you draw your curve, you're always marking your X and your Z values down here and your probability or percentages up here. Let's look at a couple examples. So example 2 says, what is the probability that a value X is 1 standard deviation below the mean? That is, a z-score is a -1. That -1 z-score tells us it's 1 standard deviation below the mean. So in symbols, it's z equals a -1. So I'm going to mark right here is where 0 would be, and right here might be where z is equal to a -1. So I want to know the probability of z being less than a -1. So that would be shading this way. So these are, because it's a -1, we know the typical percentages without actually going to Desmos. but I'm going to show you how this works. So Desmos is going to give us the area less than a -1. And I'll show you my Desmos screen. It is right here. So I'm going to turn that one on, and I'm going to, and it's nice too because Desmos will draw the curve so you can make sure that your curve is matching what's on Desmos. And we're looking at the probability of z being less than a -1, which is what we would agree with is approximately about the same as in our empirical rule, which is 0.1587 or approximately 15.87%. Now remember, we did say it's not going to be exactly what our empirical rule says. It's just going to be close. So let's find another one. What is the probability that a z-score would be bigger than 2.3? So that means we're going to, there's our 0, and there would be 1, and there would be 2. So I'm going to say 2.3 is right about here. And we want greater than 2.3. So that means we're going to use the normal dist. I'm going to write it here on the paper. So I suggest that you do as well. Of 0 and 1 because we're describing the normal z. And we want to have our min. This time our min is at the 2.3 and our max will be at the positive infinity. Now, if you don't put anything there, it'll automatically put a positive infinity. And because we're doing greater than, that's why our minimum is at the 2.3, and then we're shading to the right. Let's go to Desmos to see this. So this time, I'm going to put 2 point. I'm going to leave that one, actually. And we'll do a new one. So this time, I'm going to do 2.3. I'm going to turn off my graph up here, and then I'm going to turn on my purple one. And you can see it's right here. It's the 2.3. See where my mouse is over here on the right. So the probability that a value would have a z-score that's greater than 2.3 is about 0.0107, which is also about 1.07%. Which is considered unusual. So remember back in our lessons back in chapter 3, we talked about what is unusual, and we talked about what is unusual percentage-wise in our probability chapter of chapter 4. And so because this is less than 5%, this would be considered unusual. Okay. And we also know that too, because we said outside of 2 standard deviations is unusual. So that ties in exactly with percentage-wise, also is in agreement with our empirical rule of outside of 2 standard deviations. Okay, let's look at the next one. What is the probability that a z-score will be less than a -1.8? So again, there's my 0, there's my -1. And so I'm going to say -1.8 is out here. And it says less than a -1.8. So that means we're shading to the left. And so this time my min is going to be the negative infinity. And my max will be the -1.8. And I'll show you that on Desmos. And so I'm going to put a -1.8. And I'm going to turn off my other graph, but you can see there. Here's my gray graph here, my new one. And Desmos can also do betweens when we're talking about the normal curve and the area. So if you look at example 5, It's asking what is the probability that a z-score would be between a negative 2.68, that's going to be out here somewhere, and a positive 1.83. So 0, 0, 1, and 1.83. So we're going to say right about here, 1.83. And of course, we're just guesstimating what seems reasonable, and hopefully it looks like this. So we're saying what is in between. So let's see what percentage of observations would be between these two markings in our z-score. So let's go to Desmos. And I'm going to create another one and turn that one off and hit make sure you're always hitting the cumulative. And there's my full picture right now, but we want to be between a negative 2.68 and 1.83. And there's my shaded area. And it looks like 0.9627, which is approximately 96.27% of the data. This most makes it so nice and easy for us to find these probabilities. So there is the percentage of data that falls between those two standard deviations. Okay. So let's just go through how to read some graphs for a minute, because we're gonna have to know the left side versus the right side. If the area to the left is 0.228, then the area to the right is 1 minus that. And we could find that in Desmos too. And that comes up to be 0.9772. And then example 7 says that the area to the right is 0.122. Actually, I just have 0.12. Then 0.122. Then our area to the left is going to be 1 minus 0.0122. And again, we can find that in Desmos. And that comes up to be 0.9878. The unshaded part is 0.9878. They have to add the 1. Okay. Sometimes we are given area and we want to know what z-score would match the area, or we're given percentage and we want to know what z-score matches their percentage. So in that case, we're doing the inverse, and that's up here, inverse normal CDF. So we're going to tell inverse CDF of the normal distribution, defined as 0 and 1, and we have to give it the area to the left, even though we might be wanting to find the area to the right, okay? And we're going to have a little notation here on what they want to define. That notation is called Z of alpha. And we pronounce that Z of alpha. So in this case, alpha is always going to be between 0 and 1. Z of alpha is the area to the right. A negative Z of alpha is the Z that's area to the left. Okay, so let's just go to example 8 so we can see how this works. It says find the z-score for the following situations for the standard normal curve. Round the z-scores to 2 decimal places. We want to know the negative z of alpha 0.02. So we want to know area 0.02, but we want the negative. So that means we want the left one. So we want to know this, where the area is 0.02. So the z is in question. So we want a z that's less than something that's equal to 0.02. And it's less than because it's the left tail, okay? And in Desmos, Desmos only accepts area to the left. So we are going to type the inverse CDF. Let's go to Desmos so you can see this. And example 8. And so we're going to type inverse CDF of, and then I can paste my normal distribution right there, and then a comma, and my area to the left, 0.02, parentheses. Now, the only disappointing thing about the inverse CDF is it doesn't draw the graph, okay? But we can reverse it to check if we want to make sure we did the right thing. So we do have a negative z-score. That would make sense because we're looking for the area to the left. Okay, so if I want to check to make sure this is the picture that I drew in my paper, I could go ahead and put in my normal distribution, click the cumulative, and then put in max at negative 2.0537489. I could type in what we have as our answer here. And I can see that it did, in fact, draw the picture that I verified. So I'm just verifying. So let's just make a note. Verifying below that the graph matches. Okay. There. So our z-score is negative 2.05. We'll go 3 decimal. Let's say 2 decimal places. So negative 2.05. So let's go back to our paper so you can see where I would write this. And so it's a negative 2.05. And so the probability that your z is less than a negative 2.05 is about 2%. Let's look at the next one. It says z of 0.0. So because it's z is positive and unset positive, we're talking about 0.08 on the right-hand side. So we want to know, is it greater than this time? So the probability that z is greater than something is equal to 0.08. So let's go to Desmos to look for what z-score would signify when there's area of 8% or 0.08 greater than that z value. And so I'm going to go up here and I'm going to copy my inverse CDF and paste that. And this time, because I want area on the right, I have to enter area on the left. So I can say 1 minus the area that I want. And so that will give me a positive z-score. And we would expect a positive z-score because we were talking about area on the right. 1.405 is going to give us a z-score of 1.41 when we round to 2 decimal places. So z should equal 1.41. And again, we can verify that if we were to put in the normal curve and start at the 1.41 and go to infinity, it would give us 0.079. If we did more decimal places, 1.405, then it rounds to the 0.08, but it just validates that's what we wanted. So 0.08 is equivalent to 1.41 z-scores. Example 9 says, find the z-score that corresponds to the given area. So the area is on the right that we're looking at, 0.0461. So z of 0.0461 equals what? And we want to find that z-score. So we're going to use the inverse because we're trying to find this z value here. Let's go back to Desmos, and I'm going to copy this inverse PDF. I'm going to paste that here. And because we are given area on the right, we have to say 1 minus that and type that in, and we're given a z-score of 1.68. Let's go to B. We said, find the z-scores that cut out the symmetric middle 90%. Well, if we can do some estimating before we actually find these. If we use our empirical rule that we've been working with, we know where 68% of the data falls, or just over, so 68.26%. And we know that there's an additional 28%, so about 95% fall here, right? So it's going to be somewhere between -1 standard deviations and 1 standard deviation to get the 90, because this is 95%. So we want the middle 90%. So middle 90% means that we're going to take 1 minus the 0.9, and then there's going to be 10% or 0.10 on either side. So, or approximately 0.10 divided by 2, because we want those sides to be symmetric. So there's going to be 0.05 over here and 0.05 over here. And we want to find the negative z and the positive z that marks those. So that means there's 5% to the left and 5% to the right. And then there's 0.9 or 90% in the middle. These add to 1. And because they're symmetric, it's just going to be a plus or minus. So we can find z of 0.05, and we know that we're looking at the plus and minus of those. Let's go to Desmos and see what we can come up with. So I can do 1 minus 0.05. And notice, because z is symmetric, that I can also just do 0.05. They're just going to be the positive and minus of each other. This top one right here is the area on the right, the positive z-score. And this one down here is the area on the left, or the negative z-score. So 1.64. So plus or minus 1.64. And these are going to look familiar later on, and we start working in chapter 7, 8, and 9, because these are going to be critical z's that we're going to use quite a bit when we move into our later lessons. So this is a negative 1.64, and this is a positive 1.64. Let me know if you have any other questions.